Thank you very much for the invitation. And I must confess that these One World are some of the earliest talk I ever give, but it's a nice thing to wake up to. So I wasn't quite sure who the audience or what the audience background was going to be. So I'm going to start slowly, and I want to talk about some joint work at the end with Ackman, Hoffman, and Martel, but there will be a long story on the way. So let's see how this works. So the motivation is, if you have an operator L, which is a perturbation of the Laplacian, and I will make all of these things clear, what can be said about the properties of the solution of L by comparison to the properties of harmonic functions? So if one operator is close to another, are the solutions at all related, or in what way? So from the PDE class, what's the motivation? We all know, we're told that we understand the Laplacian very well. And basically, we're also told that solutions to nice operators on nice domains behave nicely at the boundary. And so part of what we want to understand in this talk is all these blue nice here that you see. So the question, the more precise question, which is not precise yet, is given a domain, do solutions to operators that are perturbations, we'll talk about what perturbation means, of the Laplacian, behave like harmonic functions at the boundary? So that's the question. So let me start with the problem we want to study. And so let's take omega as a bounded domain, f a continuous function at the boundary. And the question, of course, the classical Dirichlet problem, is whether there exists a function which is continuous all the way to the boundary, such that L of u is 0 in omega. I'll tell you who L is in a second, and u equals f at the boundary. And we all, when we think of a boundary, we think of a nice boundary. We'll see some that are not necessarily as nice, but. And L so is a divergence form operator, which is uniformly elliptic, and we assume it has bounded measurable coefficients. Part of the talk, we will not need that this is a symmetric matrix. We'll address that, okay? But it's elliptic. They're all elliptic, uniformly elliptic. So I remind you, if A is the Laplacian, the identity, we have the Laplacian, and in general, think of L as a variable coefficient version of the Laplacian. Okay, so what do we care about? So I'm going to remind, I'm sure this is familiar to all of you, but I'm going to remind you what we know already. And Monica, I'm assuming there's a chat manager and somebody tells me when there's questions, correct?
Yes, we usually ask a question at the end, but by the way, there is a question by Andre, and he's, well, they are asking, are the coefficients real?
Yes, thank you. All my coefficients are real valued, yeah. And I'm fine if, I mean, I don't want to change how you do things, but if people want to put questions in the chart and you interrupt, that's perfectly fine. That's how I do it in class, and so it works, okay? Okay, so what do we know? So the classical things is we know interior regularity. U is Holder continuous in omega. That's the Georgi-Nash-Moser. The nicer A is, the nicer the solutions are. So if A is smooth, the solutions are smooth, and there's in-betweens. So therefore, we're asking a boundary regularity question. I mean, we're going to focus at the boundary. And now the question is, how do we assess nice behavior of solutions at the boundary? Remember, omega, our bounded domain, is not necessarily the ball. It could be something else. So in the next slide, little by little, we will understand how to assess behavior and nice behaviors of solutions at the boundary. And then we'll talk about what the domains look like. So elliptic measures. So we say that a domain is regular, and if you want, remember what happened. I asked for every f that is continuous at the boundary, can you find a solution that is continuous all the way to the boundary? And we all know that the formulation of the PDE I put was a weak formulation. I was looking initially for W12 solution. So what does it mean that the solution is exactly, I should say, I didn't realize the typo, U is F sorry, the solution UF equals U is continues all the way there. And I should have said we're interested, I remind you, on U of F equals F on the boundary. And so the question is, what on earth does it mean that, that this W12 solution equals something specific on a set of lower dimensions? So we say that it's regular if we manage to do this. We're not asking how. How do you know whether a domain is regular? So this is a property of the domain. Wiener in 1924 gave a characterization of regular domains for the Laplacian. It's a characterization in terms of the two capacity. It's an incredible characterization because it tells you a point. You have the equality that you want at a point if and only if a condition holds, but it's not a condition that's very easy to check. But nevertheless, it's a characterization. Then in 1963, Littman, Stampacchia, and Weinberger showed that if a domain is regular for the Laplacian, then it's regular for any operator L, and vice versa. So the property of being regular with respect to a second order divergence form operator is a property of the domain. And then if we have a regular domain by the maximum principle, so we all know that we have the maximum principle, the maximum occurs at the boundary, and then the Ries representation theorem, we know that there's a family of probability measures such that we can write the solution U of X as the integral over the boundary of F of Q d omega L X of Q. So you might be familiar with these for the Laplacian. So let me make a, for the Laplacian, if L is the Laplacian, we are simply talking omega L is a harmonic measure. Sorry. And I remind you that it's measuring the probability that if you start a random walk, and if this is the set E, omega X Laplacian of E is the probability that a random walk, let me change this color, that the random walk that starts here will first hit the boundary at a point E. So it's a probability measure. And what you should think of the elliptic measure is something similar in a medium that's not homogeneous. Okay. So, and the key point is that these elliptic measures are the building blocks for all the solutions. So you see, you change F, but you still have, this is your building block. Some properties. So omega Lx, this is the L elliptic measure with pole X. And if L is the Laplacian, we have the harmonic measure as in the previous picture. And then something that's important to know, if the domain is regular and it is connected, then by the Harnack principle, we know that omega L of X and omega L of Y are mutually absolutely continuous. And in this talk, we're only interested on that type, on properties that go along these lines. So we will very soon, like now, drop the X and the Y and just talk about the elliptic measure with the understanding that whatever property we have for one point pole, we have for the other pole with a slightly different constants, okay? So omega L determines the behavior of U at the boundary. So let me remind you what we want to do. What we want to do is look if L is an operator that's very close to the Laplacian in some sense. Are the properties of U at the boundary closely related, and U is the solution to that operator, are the properties of U at the boundary similar to the properties of the related harmonic function? And so clearly the elliptic measure has to play a role because that's what the boundary sees. Okay, questions? So I started this slide with omega is regular. So let me give you some examples of regular domains. So smooth domains are regular. So I'm not maybe my favorite smooth domain, and some of the results is this guy, and some of the results we'll talk about today are new even for this case. A Lipschitz domain. So let me remind you, well, sorry. Let me remind you what I mean by a Lipschitz domain. So a Lipschitz domain is a domain that can be written as a graph, as the area above a graph of a Lipschitz function. So this is, and since I want my domain to be, this is a Lipschitz domain, so is the area, locally the area above a graph of a Lipschitz function. From my point of view, this is as nice as a smooth domain. So just so you see what sort of magnifying glass I'm using. Non-tangentially accessible domains. And why do I mention these? These are very important domains that were introduced by Jerison and Koenig. And I think in some sense were the beginning of understanding the behavior of solutions to PDEs on very non-smooth domains. So what's a non-tangentially accessible domain? I'm going to give you a picture definition, is easier. And so a non-tangentially accessible domain has three properties. It satisfies the corkscrew condition. And so what's the corkscrew condition? Is the following. You have, this is your domain here. For every point of the boundary and every radius small enough but uniform, when you draw a ball, you can find a point here. And this point has the following property. So if this is R, the ball around this ball is of radius R over M, and M is fixed. So so we look at the picture, and the properties is what you see in the picture. For every point Q and every radius R, there's a point that has distance comparable, the distance between A and Q is similar to the distance of A to the boundary, and we can put a ball around. That's a way. So omega satisfies the corkscrew condition, and so omega and omega complement satisfy these. Let me give you, so it happens inside, it happens outside. So in green, you will see things that do not satisfy this property. So one of the things we're trying to avoid is this, a cusp, okay? So this point here, you don't have a corkscrew because the size of a ball here will be way smaller when the radius is small. And then it satisfies also the Harnack chain condition. Okay, so what does that mean? It means that every time you take, this is omega, every time you take 2 points inside your domain, you can join them by a chain of balls that look this way. So what are the properties of these balls? The distance between the ball and the boundary is always comparable to the radius of the ball. And there are not too many of these balls. The length of this chain depends on the ratio between the relative distance of these 2 points and their distance to the boundary. And if you think from a PDE point of view, why do you want this? Because this allows you to have Harnack inequality in a controlled way. Okay, so who is not, again in green, who is not, no, not Harnack chains is the following. Domain, because here you have 1 point, these 2 points, if you want, are very close geographically, in the sense they're very close to each other with respect to the boundary, but to go between one and the other along the boundary, you will have to, along the domain, you will have to go here, and that's a very long chain. Okay, so I'm spending time on this because we will use this domain. In fact, we're going to use a subset of these conditions. Okay, so these were NTA domains. I will explain in a later slide where they appear and how they appear, but As I said, this was Jerison and Koenig. Okay, so this is an example of a very beautiful Wiener regular domain. Then we have core-dark domains. So the core-dark domain is an NTA domain plus, if we live in Rn, the surface measure, so Hn minus 1 restricted to the boundary of omega, is Alfors regular. I'll tell you what that means. And so Alfors regular means that there is a constant such that the boundary of omega intersection every ball with radius small enough. Sorry, let me write it. So for people who have never seen these, are n minus 1 and C0 are n minus 1. So basically, the boundary balls have the right Euclidean growth. Okay, so is NTA plus has this property. Again, this is a very nice Wiener regular domain. In fact, it's uniformly Wiener regular. I'll explain how. And then these are the domains we are going to really be interested on. There are, so let me go back just for the experts. These up to now, all the domain, well, not the NTA domains, but this domain here, it's, they're uniformly rectifiable, they're irrectifiable, their boundaries. And now I want to talk about uniform domains satisfying the CDC condition. So what is that? That is a domain omega that satisfies corkscrew, not for the complement, just for the corkscrew condition, to Harnack chain. And 3 was the CDC condition, is a quantitative version of Wiener's quantum. So quantitative version of Wiener's condition. Okay, but to be dramatic in some sense, I want to, so if we have a domain, so uniform, these are the two conditions for the uniform domain. Okay. And I should say Aikawa has beautiful work on the behavior of harmonic measure on these domains. But basically, if you have these two conditions and you have that the green condition, the Alfors regularity question, you don't have a rectifiable boundary. So the exterior of the four-corner Cantor set in the plane satisfies that conditions. So, and then having the CDC is even a weaker condition than having Alfors regular boundary. So here we are talking about rather non-smooth domains in some sense, okay? So here is my slew of regular domains. Why do I present them all? Because as you can imagine, in the development of any field, it starts with smooth and Lipschitz, and then you go all the way to here. And so in some sense, one of the things we're going to talk about are some results that are common to all of these domains. So questions on who my domains are going to be. And in general, these are the domains that I am going to be focusing on, the uniform domains with the CDC condition. Okay, so where did this start? So in 1970, Hunt and Whedon proved the following result. So they were looking at harmonic measure on Lipschitz domain, and they proved that on a Lipschitz domain, the harmonic measure is doubling. That means there exists a constant such that you can always bound the harmonic measure of the ball of radius 2r and center q in the boundary by the measure of the ball with the same center and radius simply r. And it was partially in looking at this result and the tools of the proof, of course they use Lipschitz, but that Jerison and Koenig realized that one didn't need to have Lipschitz, that it was enough to have NTA domains. So that was one of the big motivations, I think, to understand, to introduce NTA domains. So these holds also on NTA domains. But so please keep that in mind. But so a little bit later, Dalberg proved that on a Lipschitz domain, more than this is true. That in fact, it means that I will explain or I will remind you what this means. It tells you that omega is absolutely continuous with respect to sigma and vice versa, and that there's a quantitative estimate. Okay, so let me tell you what that is. Before, let me tell you how that extends. So David and Jerrison and then independently Sands in 1991 proved that if omega is a core dark domain, I remind you what this is an NTA domain that has alpha's regular boundary, then omega is an A infinity weight. And now let's do the A infinity. I remind you what this is. So omega is an A infinity weight if omega is quantitatively absolutely continuous with respect to sigma. And that might be a useless sentence unless I explain. And that tells you that for every epsilon and every delta, if you find a Q in the boundary and a radius that's between 0 and the diameter, and you look at the surface ball, so, okay, this is your surface ball. And now you take a small set inside, the green thing is your small set, okay? And that if you choose the ratio of the surface measured of E over the surface measured of the ball small enough, then the harmonic measured of E over the harmonic measured of the ball is as small as you want, okay? So of course, if you show that it means absolute continuity, which means if one of them is 0, omega of E is 0, sigma of E is 0, and vice versa. It doesn't show that's vice versa, but it is true here. But it's more is a relative size thing, okay? Okay, so this was, in many ways, I think I consider these two results the beginning of this area in which the results that I'm going to talk about lie. So, of course, the first, and again, you know, I always say this because it reminds me of the PDE class. When I teach the students, I tell you, well, we're going to talk about the Laplacian for the first PDE class. And then you tell them, and every other divergence, symmetric divergence form operator is very similar. And so I think along those lines, the first question that was asked right after Dalberg proved this is, well, and he did prove more, and we'll touch upon that in a second. Does the same thing holds, not for the harmonic measure, but for the elliptic measure that I introduced earlier. And then, so that was the question. And then very soon after, there were different works, one by Caffarelli, Fabes, and Koenig, other examples by Modica and Mortola, and by Modica, Mortola, and Salsa in 1981. And all these examples are different. They showed that there exist Lipschitz domains and operators L, for which omega L and sigma are mutually singular. So basically, they're supported in completely separate disjoint sets. I mean, in quotations. And you might be thinking, oh, but is a Lipschitz domain? In fact, the examples of Caffarelli, Fabes, and Koenig, the Lipschitz domain is the ball. And the operators are actually, the operators have continuous coefficients. So clearly things are very subtle, okay? It's not that, it's something serious is going on. So the first question, once you want your dreams destroyed, you start wondering, okay, well, is there a way that I can characterize the operators L for which omega L is an A infinity weight? And then, so that was the initial question. And then in recent years, we've started thinking about, for those operators for which omega L is an infinity weight, does that give us any sort of information about the geometry of the domain? So, and some of you might have heard me give talks about these lines, and then this is the place where some of my talks diverge. In a different talk, I will be talking about the second question. here we want to talk, well, more about questions that come from the first question. So this has created a number of different approaches. And so the approach we're going to talk about is perturbation theory. So I won't talk in this summary about it. We'll see it in detail afterwards. But there are many approaches that have been used to understand the question of, can you characterize, if I give you an operator L, do I know where omega L is whether omega L is an infinity weight or not? So some of the results depend on the structure of the matrix. So let me give you two very rough examples. Imagine your domain is the ball and you say, well, if the matrix is radially only depends on the radial variable, then okay. Or if your matrix, or if you are on the upper half plane and your matrix is independent of T. So conditions on the matrix A. There's a big industry on looking at the oscillation of the matrix. So not if the matrix is smooth, but if it oscillates well in a quantitative way. These are conditions on the oscillation on the matrix, on the gradient of the matrix. So that's another avenue of research. There are also properties of the solutions. There's results along the lines if every time you choose you have solutions which are bounded by one at the boundary, then the following thing happens, then can you say something? There's a funny one. If somehow, and you might say this is not very useful, you know the behavior of A and the elliptic measure, so you want to understand one domain, and then you know how that operator behaves with respect to all Lipschitz domains, which are interior to the domain you're studying and whose boundaries coincide, then somehow you can transfer the results to the domain you started with. And this, I put it kind of in italics because it looks a little bit mysterious, but is a very useful tool. Okay, so for the rest of the talk, we are going to focus on the perturbation theory. Okay, and how the perturbation theory has been used to address the question of whether omega L is an infinity with respect to sigma, and where that study has led us. So everything comes from the following observation. If the behavior of A, the matrix, near the boundary determines what happens to omega L with respect to sigma. So let me draw a picture of this remark. So imagine you have two operators, L0 and L1, and you assume that somehow A0 and A1 coincide on the neighborhood of the boundary. So this is omega here. And we are assuming, and it's just inside, remember that there is a neighborhood of the boundary. Okay, so sorry. That in this area, so here, A1 equals A0. Okay, so afterwards they're, inside here, they're whatever, but near the boundary and everything is colored, sorry about that. And so what this tells us is omega 0 is an infinity weight with respect to sigma, omega 1 is also, and vice versa. Okay, and I also put these, so let me take this as a time to introduce what it means to be a BQ weight. It will not play an enormous role, but for those of you who know it, I think it completes the picture. So we say that omega is a BQ weight with respect to sigma, if and only if I call K equals, so remember, being A infinity, means you are mutually absolutely continuous. So you take the radon-nicodime derivative, and being a BQ, and Q here is bigger than 1, means that a reverse Holder inequality holds for every delta surface measure here, okay, of Q, sorry, this is Q, the sigma is bounded by a constant that depends on Q. Okay, so this is a reverse Holder inequality. And so this lies in the area of the harmonic analysis. This is a Mackenhout weight. And if you are in A infinity, it means that you belong to some BQ, and A infinity is the union of all the BQs. And you realize this is reverse Holder, so it means something about how nice K is. Okay, so the key point of this slide is, if you know that two operators coincide in the boundary, then of course what happens, they behave very nicely. So this means it only depends on the boundary, and this is one of the key ideas of the proof of the result that I want to talk about. Okay, so the idea is to define perturbation. And so we say that L1 is a perturbation of L0 if the deviation function, A of x, which is the sup of A1 of y minus A0 of y in this ball. So who is this ball? If this is omega, x is a point inside, delta x is the distance to the boundary, and I am measuring how far away. This is the ball of radius delta x over 2. Delta x over 2. I am measuring the distance between A1 and A0 in these balls, okay? And we say that L1 is the perturbation of L0 if, when we look at the sup of the difference here, it satisfies the following condition, and I'll explain what this condition is. I don't expect you to remember it offhand. A squared of x over delta x. Delta x is the distance to the boundary, is a Carlson measure, okay? So let's go to what it means to be a Carlson measure. So bear with me, we'll get there. Please don't read ahead. So this is a Carlson measure in omega. If for every time we take a point on the boundary, omega is here, we take a radius here, and we look at this ball. So this is what, this is BQR, intersection the boundary. TQR is this ball on top. And so we look, remember, this is the deviation squared over the distance to the boundary. We integrate this function over the solid area. We divide by the surface measure. Sigma is the surface measure of this piece. We divide by the surface measure. Forget the 1/2, that's not too important. This is bounded by a uniform constant. So let's think for a minute. This is a solid integral, so if there was no scaling, this should be something of order Rn, but I am dividing by Rn minus 1. So this is telling me that really there's some sort of decay here, because I need to be able to integrate. Think of it, A doesn't have a dimension. This will be a 1 over R. It's getting is blowing up at the boundary. So for this to be bounded, it's telling me that the deviation is getting very close as I'm approaching the boundary. And in fact, that's philosophically what happens. If L1 is a perturbation of L0 with this definition here, then A1 equals A0 on the boundary. So for us, you know, I started with, if L is a perturbation, this is what it means to be perturbation. So, okay, so please try to keep in mind these definition. Okay, so remember the question is how that Dalberg wanted to ask, for what operators can I say that omega L is an A infinity with respect to sigma? So Dalberg used this condition to show the following. In 1986, he proved that if this quantity is going to zero uniformly on the boundary, then omega 0 is an A infinity weight with respect to sigma, if and only if omega 1 is an A infinity weight with respect to sigma. Okay, this is a beautiful result. I mean, it has an incredible idea to be an A infinity weight, as I said, it means that during some BQ, you know that he knew that the right Q was 2, and he says, well, he basically introduces an ODE to show that the constant that if you know the constant for omega 0, then you know the constant for the omega 1, and it's a beautiful ODE to control the constant of that reverse Holder inequality. So this is a beautiful result, but it was not one that but I think people were not very happy with it, because you're assuming something enormous. You're assuming that this quantity goes to 0 to be able to prove A infinity. The sense was that one should have, if this quantity is bounded, then you're A infinity. Okay, but so Pfefferman was the first one who did something toward removing this smallness assumption here. And then it was the work of a number of people. So in the Lipschitz domain, Pfefferman, Koenig, and Pfeiffer were able to show that if this quantity is uniformly bounded, then omega 0 is an infinity weight with respect to sigma, if and only if the same thing holds for omega 1. Then with Milakis and Pfeiffer, we were able to show the same thing on core dark domains. So I have to say what we did here is show that the tools that can be used in Lipschitz domain can be developed in these domains, and it works. Then using different techniques on uniform domains which are Alfors regular. So now, then Cavero, Hoffman, and Martel prove the same thing. Okay, remember these domains now do not necessarily have rectifiable boundaries. Nevertheless, so this surface measure can be bad, but the relationship still works well. Okay, so what was the key tool? The main tool in the proofs of Pfefferman, Koenig, and Pfeiffer, and that I joined with Milakis and Pfeiffer, was the following thing. If you have a Lipschitz domain or a Kordak domain, there exists an epsilon 0 such that is this funny looking thing. So let me explain what this funny looking thing is. A squared is the deviation. G0 is the Green's function with respect to the operator L0. And now I'm divided by delta squared. I did not make a mistake, there's a square. So I integrate that on the tent, on the solid ball inside, and I divide by 1 over omega 0 of delta. The tool is, if this is uniformly small, then omega 1 is in omega 0 and belonging to B. And so then it's easy from there to say, well, if omega 0 is an A infinity with respect to sigma, and omega 1 is an A infinity with respect to omega 0, then it's translated, there's a translation and it works. So this was the key tool. So even if the tool is not very clear to you yet, I want to focus on something. We start with either a Lipschitz domain or a Kordak domain where the surface measure behaves well. And you look at this condition and the surface measure of the boundary is nowhere to be found, correct? So the question is, why do we need a surface measure to behave well to be able to do these? And the truth is because in the proofs, we used the surface measure. It was hidden there, but it was crucial. But that's what we started wondering about, okay? So here, G0 denotes the Green's function of L0 with a point that's roughly inside, and this is who everybody are. So again, looking every time you have a theorem with a hypothesis that does not appear to be used in the conclusion, one wonders. And so that's what I wanted to talk about. So this is the main result I wanted to discuss. This is joint work with Murat Akman, Steve Hoffman, and Chema Martel. And let's take a uniform domain satisfying the CDC. So this is a domain. Do I have a question, Monica?
Yes, let me. So Alexander Nazarov has a question,
Yeah.
and you can ask.
Tatiana, please, what is a green function? I know that the green function has two arguments, and you say one.
Yeah, thank you. So I am hiding here. So I have a domain omega. Remember my domains. I take any point. In fact, so how big is the size of the ball depends on the ball. But when I say G0, so I am assuming I'm fixing a point inside. Okay. And,
Okay.
and
Okay.
so
It is the green function with respect to this point. Yeah.
to this point, but this point roughly can be any point far from the boundary, and
I
all
see.
my estimates depend on far from the boundary.
Okay. Thank you.
You're welcome. Thanks for the question. Okay, so we have our uniform domain with the CDC. Again, remember, not even a surface measure, which is what I was saying, seemed to not be, at least didn't appear in the statement. We have two operators, L0 and L1, which are uniformly elliptic with bounded measurable coefficients. Please notice we're not assuming they're symmetric. And we look at the deviation. And our statement says, if we look at that mysterious condition that appeared there, which is a way to define the distance from, I mean, it's not really a distance, but we call rho of A0 and A1. So if the distance between A0 and A1 in this strange sense is finite, then omega 1 is an A infinity weight with respect to omega 0. And then if you give me a P, I can find you an epsilon P such that if this distance is small enough, then omega 1 is a BP weight with respect to omega 0. So the reverse Holder inequality holds with P. Okay, so this is more, this is more consistent with the sort of thing that one would like. Bounded gives you A infinity, small gives you, this is the right notion of regularity and of being close. So let me make a couple of remarks. This result is new even in the case where you choose it. One is new even in the case where you choose a ball. Okay. So this is, in the few minutes that I have, I'm going to give you a very, very, very rough idea of how one proves something like this. Okay. So the first ingredient of the proof is that remark that I made at the beginning, that if we have two operators which coincide on a neighborhood of the boundary, then the results should be the same. So based on that, we do exactly that. You take a J and you define this AJ matrix. And what you do is the following. You remember, you define, maybe let me draw my picture, it's easier than trying to do this. I take this is my neighborhood 2 to the minus J. And then I define this A upper J to be is A1 here and A0 here. Remember, I am trying to prove that omega 1, this is what I want, okay? Omega 0. So what I am going to do in some sense, I should say, is approximate, please put big quotations in that approximation. I'm gonna approximate A1 by these AJs. You agree, I mean, this these neighborhoods becoming smaller and smaller, so that makes sense. I'm going to look at the elliptic measure of AJ, because AJ and A0 correspond on a neighborhood on the boundary. I know that the corresponding elliptic measures, are mutually absolutely continuous, and besides that, we know that there are A infinity. So if you think of it, of course I have to be lying, because, but in some sense, yes, in some sense is the basis of the idea. We are going to look at the omega j. We're going to say omega j is an A infinity weight with respect to A0. And what we would like is to get uniform estimates so that I can pass to the limit and things work. Okay, that's what we want to do. Of course, it's slightly more elaborate than that, but that's the idea. So what we do is the key of the argument, and it's carried out in two different papers, one with me, one without me, assumes that there is a Q, that we can find a Q such that omega j belongs to BQ of A0 with constants that are independent of J. Okay, and then we kind of let the omega j's, the J go to infinity, and then it should be converging to omega 1. So how do we achieve this bullet over here? Okay, the third bullet, sorry. So this distance gives rise to a discrete Carlson measure. So what does it mean? We build these boundaries are are nice enough, and we do have using what's a discrete Carlson measure is a Carlson measure roughly on cubes inside and cubes at the boundary. Okay, there are nice dyadic cubes in here, and then there is a big theorem of Hoffman and Martel. Is kind of was a big canon that you bring in and show that that the Carlson measure that you can build using these satisfy the hypothesis of the Hoffman and Martel big canon. And these allows us to decompose the operator Lj into kind of a good piece and a bad piece that one can control, and allows us to show that the omega j's are A infinity with respect just dyadic, so with respect to dyadic cubes. Okay, so and these, remember, are dyadic cubes on the boundary, and so you're asking how do we build these cubes? They're there, and then and these are, there's the dyadic, the A infinity happens to be with a constant that's independent of J. And then we use that to be able to prove that then the omega j's are in BQ weight with respect to omega 0 with a constant that is independent of J. Okay, so I am really, these are the three big steps of the proof, but there are many things that go into proving each one of the steps. So those are basically the components of the proof. As I said, the result is new even in the case where we have a smooth boundary. And so you might be wondering, what are we trying to do now? So what we're trying to do is to prove that if we look once again at this quantity, and this quantity is uniformly small, then we're trying to understand what's the relationship between omega 1 and omega 0. We're able to say that omega, so what we know is that omega 1 belongs to BQ of omega 0, basically for every Q bigger than 1. But of course, we want more. For those of you who are in the area, the right question to ask is whether the Radon-Nikodym of omega 1 with respect to omega 0 has a log that is in VMO. And that's the thing that we're trying to achieve. And then along these areas, along the areas of perturbations of this type, I want to highlight recent work of Fenouil and Poggi, who are trying to characterize operators for which A1 is an A infinity with respect to A0 using perturbation, and they're using the area integral. And this is work that comes from their work on lower dimensional boundaries. So it's a very different approach. It's not yet ready, but they have some very nice results. Okay, and so thank you very much for your attention.